This is Chad Omet with the National Weather Service here in Topeka, Kansas. Thanks for joining us for our virtual edition of our spotter training, severe weather safety and information show. With me tonight, my co-pilot is Adam Jones with the National Weather Service. Adam will be answering questions that you may have in the control panel throughout the show, and he'll be running some of the polls. If you cannot hear me, if the audio is unclear, you can try calling this phone number and access code. You don't need an audio pin, no microphone is needed. And so go ahead and try that. If you cannot hear me right now, if I'm not clear. So you can try that. The other thing about what we're doing tonight and how things work is there is a questions panel that you see here, and you can go ahead and ask questions that way, and Adam will do his best to answer any questions that you may have as you're watching the show tonight. So what I'm going to do tonight is talk a little bit about preparedness, situational awareness, mostly. New ways to receive information, stay aware of what's happening around you for your own benefit, your own safety. We'll talk a lot about storm types. Specifically, we'll talk about squall lines and supercell thunderstorms, their cloud features, the processes that lead to their formation and what they mean to get you to maybe give you a better understanding of what it is you're looking at and what you can expect. We'll talk a little bit about the role of the storm spotter in the warning decision-making process, and then finish up with some hazard safety information at the end as well. Go ahead and launch the first poll, Adam, if you can. The question for our first poll is, how many tornadoes do we have each year? And we'll see if we can get this going. So the vast majority, it looks like we're still collecting a few responses, but it looks like the majority of people have answered. And there they are. There's the results. Most of you answered 80, and that's correct. We average about 80 over the first 30 years, or the last 30 years. That's what we typically have seen here in Kansas, generally speaking, 80 tornadoes every year. 7 of the last 10 years have been below average. We've had 44 documented tornadoes last year. This was one of the tornadoes we had here in Northeast Kansas. This was up in Brown County, just south of Hiawatha. This was an EF2 tornado. I'll talk about those numbers and what they mean in a little bit. Basically, go ahead. Let's see. We're going to go ahead and close the poll, but it looks like you still see our poll. So what I'm going to try to do, there we go. So we got stuck on a poll. That's okay. This is the EF2 tornado that was up in Hiawatha last year. It's an EF2 on a scale of 0 to 5. As I mentioned before, we had about 44 documented tornadoes in the state. We average about 80. And so relatively speaking, it was a quiet year across the state of Kansas for tornadoes. Greatest danger, and let's talk more about that, obviously, is blowing and falling debris in the tornado. And so that's what we looked at last year. Here's a different view of tornadoes over the last 30 years or so. This is the Kansas tornadoes per year since 1993. You can kind of see the trends, if there are any really. It got very busy. Record year in 2008. That was the year that we had the Manhattan violent tornado EF4. Set a record that year. 2007 was the year we had Greensburg. That was our last EF5. But 7 of the last 10 years have been quieter than normal, below average numbers for tornadoes across the state of Kansas. So that's interesting. Some of the mortality data over the last 20 years, the state, or you can see here, the country, how it looks. We've had 22 fatalities here in Kansas over the last 20 years. And most of those were from the EF5 in Greensburg back in 2007. This also captures the year 2011. We had 558 people perish from violent tornadoes hitting large cities. It's the year Joplin happened. And we had some big tornadoes in Mississippi and Alabama as well. That's what the way the last 20 years have looked. This is the way the last 10 years have looked. Now, people look at this and they ask, well, does that mean that we have the same risk from tornadoes as Nevada? No, of course not. We still have a very high risk, relatively speaking, across the country from tornadoes. But we haven't had any fatalities. Why so many to the south and east of us? A lot of people are asking, is Tornado Alley shifting to the southeast? You could say, in a sense, in the last 15 years, there's been an expansion, but not a shift away from Kansas. One of the reasons so many people have lost their lives in the southeast is that population density is higher down to the southeast. More people live in mobile homes in the southeast, and more tornadoes occur at night in the southeast. And so all of those things conspire to raise the risk and increase vulnerability from tornadoes in this part of the country. Whereas where we're at here, most of our tornadoes occur before we go to bed. This is a kind of a busy map, and I apologize. The takeaway from this is the yellow, the orange, and the red lines indicate what are strong and or violent tornadoes. And we've had at least 40, actually 44. It says 40. We've had 44 of these in the last 10 years across the state of Kansas, including the May of 2016 tornado that was an EF4 that missed Chapman by a little bit just to the southeast, and then the May of 2019 tornado that missed or hit parts of southeastern Lawrence as well. So we've had our share of what we call strong and or violent tornadoes the last 10 years, but thankfully no fatalities. So the question is, is our risk going away? No, it's not. In fact, you look at the average number of tornadoes through 2021, and we're still number 2 by sheer numbers of documented tornadoes across the country. You take into consideration the size of the state, and we're still pretty close to number 1 or 2. Certainly, if this was a basketball tournament, Kansas would be a number 1 seed when it comes to documented tornadoes every year. So the risk has not gone away. This has not changed over the years. Pretty typical. If you lived in Kansas, you know that April, May, June are our peak months of the year for tornadoes. We've already had one event with a couple of tornadoes in March. This time of the year, we tend to not have sufficient moisture. That's one of the things that's challenging to get more supercellular tornadoes. But as we head into the months of April, May, and certainly June, we start to see better dew points moving further north, and that supports those organized thunderstorms like supercells. And this is, I think, good news for Kansas compared to the southeast, is that the majority of our tornadoes happen in the evening hours. This is local standard time, so basically late afternoon into the evening hours. And by the time we hit midnight, there's a dramatic drop off. That's not the case in the southeast. A lot of their tornadoes are occurring not only after dark, but after people go to bed, after midnight. And then one of the reasons that the risk is so high in the southeast, and the numbers of fatalities are a lot higher down to the southeast as well. So before the storm, we want to quickly talk about putting together a plan, practicing the plan, having a few different ways to receive warning information. Number one, part of the plan is knowing where you're going to shelter at home, work, or school. Where are you going to go? What's the plan? If you live in a mobile home, do you have a community shelter? These are questions to ask now before the storm. At your business, what's the plan? Where would you go in the event that a tornado warning is issued? How long does it take to get there? Especially for those that live in mobile homes, it may take 10 minutes. Maybe they have to drive to get to the shelter, or to a neighbor or friends that has a basement. And then we talk about the importance of putting a kit together. When we go out and do damage surveys, oftentimes we will see the importance of having closed-toed shoes, the debris that is just all over the place. And certainly you want to have closed-toed shoes, flashlight, batteries, charged phone. These are all different things that you want to have. Talk about the importance of helmets. A lot of the fatalities back in 2011 were due in part to blunt force trauma to the head from falling and blowing debris. And so helmets, bike helmets, any sort of sports helmets can certainly provide protection over and above nothing at all. So this is important to remember as a part of your tornado plan. And then practice the plan. That's important as well. Again, mobile homes, we're talking vulnerable populations. Those are the most vulnerable. If you live in a mobile home, evacuating needs to be part of your plan. You cannot survive a strong or violent tornado in a mobile home. It's just not going to happen. Let's try this one more time, Adam. I might get hung up again. I'm just curious. We'll do the second poll here. I'm just curious to find out, everybody that's on right now, if you have a source of weather alerts or radar on your phone. And I'm just my own curiosity. I'm wondering how many of you do. Well, so far it looks like everybody said yeah, and that's fantastic. Certainly in this day and age, things have changed over the last 10 or 15 years, and we have a lot more resources, a lot more ways to receive information than we did even 10 or 15 years ago. And there are so many radar applications now that are available that can increase your situational awareness. So many ways to receive alerts on your phone that I think it's crazy these days to go about. And certainly if you're a spotter or you go out and you look at storms, if you don't have a source of radar, that's absolutely insane. And so having a source of radar is critical. Having another source of alerts on your phone is also very, very important. I'll talk about wireless emergency alerts here in a second. I think all of these, when I say the word alert, the word means just to get your attention, to stop what you're doing, and then go find out additional information. And that is best done by our local media partners. I know, it's 2024, but local television still does a fantastic job of framing visually for you where the threat is at and where it's moving, when it might get to you. And so our local TV partners, AM radio still plays an important role in broadcasting information about what's happening, where, and what you should do. So your local media partners are a very, very important component in the situational awareness. Outdoor sirens, great if you're outside. Don't rely on them if you're inside for that alert to go find out what's going on. NOAA weather radio has been around, it seems like, for 100 years. It still can provide sort of that gap, sort of that emergency gap coverage for those areas where maybe the cellular coverage isn't very good. But weather radio still exists, and one of the fastest way to receive warning information out there as well. And honestly, this last one, from friends and coworkers, people might sort of scratch their head when I say that, but when we go out and do damage surveys after a tornado and we ask people, how did you receive the warning? Many of them now say, my phone started making a crazy sound, but then my sister called me, my brother-in-law, whatever it might be. And we just heard this on Wednesday that I got the alert on my phone, and I thought it was a mistake because there was just raining, just light rain at the time, and I thought they meant Wabunsee County, not Shawnee County. And I called my sister, and she said, yeah, that's for you. That storm's moving up towards your way. And so this happens. It happens a lot. It's how people personalize the risk or the threat and actually get to the point where they take shelter. That noise, the noise. This has been around for 7 or 8 years. This is a program that is done through FEMA. It's an opt-out program, meaning when you buy a phone, it is turned on automatically. You'll receive, I think probably we've all received Amber Alerts. Amber Alerts are another component of this. Other federal agencies use this program. The Weather Service itself will only use the WEA system for tornado warnings, serious flash flood warnings, and severe thunderstorm warnings that have either 80-mile-an-hour winds or baseball-sized hail or larger within the warning itself. That's what triggers WEA. when it comes to the weather alerts, the weather warnings. And so that severe thunderstorm, the high-end severe thunderstorm, is a little bit new. It's just in the last couple of years that we've started to do that. We issued 7 of those here in the Weather Service in Topeka last year. Most of them were for wind. We had a lot of strong damaging downburst winds or downdraft winds here. And so we issued more than I expected last year. Real fast, talking about situational awareness, outlook information. Let's go back to last Wednesday. If you were in Northeast Kansas, we had tornadoes here. So let's talk about some of the information that was available before the storms developed, early in the morning. Information that's available, weather.gov. We provide a briefing packet, briefing information that provides information, sort of a what, where, when for what's expected. It looks like this. This is what it looked like last Wednesday at 9 o'clock in the morning. We have risk areas outlined in colors and words that describe the risk areas and what to expect, general timing of what's expected, talking about very large hail, damaging winds, a few tornadoes possible near a warm front. We'll talk more about warm fronts because they are notorious when it comes to tornadoes in Northeast Kansas. And so this is information that's available off of our website. And before the storms developed, the day of, you might want to check our website, check out what we're thinking, what's going to happen, or what we're expecting to happen later on that day as well. The Storm Prediction Center is another organization that will provide situational awareness information for people, outlook information. They draw areas, and based on the probability of bad things like tornadoes or very large hail, they will use words to describe the risk like enhanced, moderate, high, and they'll draw areas not only for today, but over the next 7 days where they believe there is a risk for severe thunderstorms. And those are what the colors and the words mean. Again, they're just trying to reflect the probability of different hazards occurring as well. And so the Storm Prediction Center does a really good job, and it's another potential resource, if you're curious, to look at not only for what's possible today, but over the next several days as well. So let's go back to last Wednesday, and the tornado watch comes out. Whoops. My PowerPoint just crashed on me. Let's do this. Technical glitches. What are you going to do? We'll get it going again. I think I was right about here, and we'll just get going from this point right here. There we go. What are you going to do? Technology. So a watch, last Wednesday, a watch came out around 5:30, 6 o'clock at night. It means that basically we expect storms to develop, maybe not immediately, but over the next few hours. Closely monitor weather situation. Maybe start paying attention to that weather app that you've got, looking at our website for additional information as well. Social media updates. We are on social media. The app formerly known as Twitter, X now, is something that is actually pretty useful for sharing information during severe weather. We found that a lot of, you can tag us at NWS Topeka, and we'll be able to see your reports or use the hashtag KSWeather, KSWX. Those are useful, and I'll show you that here in a little bit. There are other pieces of information that our office provides. This is what we provided last Wednesday at around 6 p.m. using tools that we have here like visible satellite imagery and our observational network that we have here. We can see with certainly the visible satellite imagery, and looking at that, we can tell certain areas where storms are most likely to develop. And so we were able to, between the watch and the warning, so sometimes people say there's a gap in between those two, and we're able to try to fill that gap with additional information for situational awareness that, hey, this is the area in through here. If you're in Wabaunsee County, Shawnee County, Morris County, Southern Geary County, in that area, watch out over the next couple of hours. We think storms are going to develop, and they could produce bad things, be it big hail or tornadoes. And so this is information, another example of what we provided on social media before the tornadoes occurred as well. And then obviously Once a warning is issued, that's when you take your plan and put it into action. The polygons right there, the WIAs will trigger for those areas that are very close to or within that polygon itself. And so that's what we want to do. That's the difference between the watch and the warning. The warnings put your plan into action, take shelter. The watches stay aware, be on guard, start paying better attention to your sources of information as well. So let's talk more about thunderstorm types and the associated cloud features. I do want to touch on thunderstorm formation and the ingredients that we need for thunderstorms to form. The first, I mentioned before, this time of year, it's difficult to get your classic supercellular tornadoes. Even though we did on Wednesday, there were a couple of things that came together to help that happen. And one of them usually is this time of the year, we struggle with moisture. And the other two are instability and lift. But first, I'll talk about moisture. And here's another poll. Adam, let's do it. Let's try and see if we crash it again. But let's go ahead and launch another poll and see what everybody has to say about this one. So as a rule of thumb, what's the lower limit of dew points that we typically need in Northeast Kansas to get supercell tornadoes? I'm curious to see what you have to say. It's changing. Looks like the majority of people got it right. And yeah, I think that's what it looks like. The majority of people said 55. That's right. It's a rule of thumb, but this is one of the things that we look at when it comes to certainly supercell tornadoes is the buoyancy, the amount of moisture that we need from the Gulf of Mexico to help us get those thunderstorms to form. Let's see if we can get this to close out and allow everybody to see my next slide here. Yes, there it is. Our moisture source is the Gulf of Mexico. Pay attention to the dew points. The dew points available on your weather apps, the dew points available on the evening or the morning broadcast television. And watch those dew points. We, generally speaking, want at least dew points in the mid 50s, mid to upper 50s. Now, why is that? The cloud bases are one reason. You get dew points that are lower than that. Your downdrafts with thunderstorms tend to be a lot stronger and colder and can destroy the low level circulation. So there's a lot going on when you have dew points that are lower that don't support the development of certainly supercell tornadoes. We had dew points in the mid to upper 50s on Wednesday, but we also had a warm front that actually helped to combine with that moisture to help us get those supercell tornadoes. And we'll talk a little bit more about why that is here in a second. So yeah, you need really dew points from the Gulf of Mexico, at least in the mid 50s. And then you need instability, buoyancy. And how do we get that? We can get that a couple of different ways. We can cool the atmosphere aloft from storm systems that are moving in. We can also warm the atmosphere in the low levels, which is typically what happens at any given day, where the sun heats the ground heats the atmosphere near the ground, and we cause these little bubbles of air to start to rise, and they may cool and condense and form clouds. But there's oftentimes a lid of very warm air that acts as a cap and doesn't allow these parcels of air, these bubbles of air, to keep rising, and acts like a lid. And sometimes through just continued heating of the ground and the atmosphere in the low levels, we'll punch through that cap. It'll weaken enough to get thunderstorms to form. But oftentimes we also need some form of lift in the form of a warm front, in the form of a dry line or a cold front. And it's the heating together with that lift that helps us, along with the sufficient moisture, to get thunderstorms to form. And then based on the amount of buoyancy and the wind shear that we have in place, we can get different kinds of thunderstorms. The thunderstorm life cycle, obviously updraft stage, when basically the thunderstorm is just forming, it looks like a big old fist of cauliflower if it's a very strong updraft punching up into the sky. Eventually you start to form rain or hail, and that starts to fall out of the cloud and down, evaporates, cools the air around it, drags it down even more, and you have a downdraft. You have an updraft and a downdraft. There are different clouds that form based on those different processes, the process of inflow and updraft, and downdraft and outflow. I'm going to talk about that here shortly. And then downdraft, eventually we lose our lift and it's all downdraft, the cloud evaporates and it's gone. And so we're going to talk about the mature stage, because the updraft and downdraft can lead to very, very different cloud formations. This is a very modest slide, but it's a very important slide, because the concept that I'm talking about here is so important when understanding the cloud features that you're looking at. When you're outside and you're looking at a storm that's moving in, and you see what looks to be a lowering underneath a base of a cloud, that may be associated with what's called inflow and updraft. Now, thunderstorms are alive. They breathe. And by that, I mean they inhale warm, humid air, and we call that inflow and updraft. And there are different cloud features associated with that. I mentioned before the updraft, the rotating updraft, lowering or wall cloud. There may be inflow bands. We call it rain-free base, the base of the updraft. All of those are associated with inflow and updraft. And where the storm exhales cold, moist air, it's called downdraft and outflow. And that process leads to a very different cloud feature. It's called the shelf cloud, which is the leading edge of a cold pool of air. And so very, very different processes lead to very different cloud features when you're out looking at these thunderstorms. And so very important concept to remember as we continue to talk about these kinds of different storms and the cloud features associated with them, because understanding the processes that are going on can help you anticipate what these storms may do or what they are doing right now. So we're going to quickly talk about pulse, line, and supercells. Pulse storms are storms essentially that form when there's very little in the way of wind shear. And so the winds up here near the anvil top of the storm may be the same as they are down near the surface, 20 or 30 miles an hour. So what goes up comes right back down on itself and collapses. The hazards with these pulse storms, I would say mostly can be just lightning and perhaps some downburst or microburst winds with a very localized, very intense downdraft, especially in July or August. If you get the right heat and humidity combination in the atmosphere, you can get what we call microbursts with these thunderstorms as well. I'm going to try to play this video. We'll see how it works. But the video on the top right shows what's called a microburst. And it's right there. It's an enhanced area of downdraft that forms within the thunderstorm and then crashes down to the ground. It's almost like a hose pointing directly down at the ground. Water spreads out everywhere. It's not just water, it's air, a lot of wind. And this can be very, very hazardous to stuff that's obviously underneath it. It can be aviation, airplanes, it can be your house. These are around, especially in July and August, but they're very small and they're difficult to detect on radar. And they're called microbursts. They're just locally damaging downdrafts of wind with these thunderstorms that form in certain atmospheric conditions. When you have a lot of heat and humidity and the winds aren't very strong in the atmosphere, you can oftentimes get those. With lines of storms, however, the difference with lines of storms is we have more wind shear in the atmosphere, a little more buoyancy, a little more wind shear. And sometimes we get these lines to form, these thunderstorms that may begin as discrete or individual storms. Maybe they're supercells that team up and they eventually evolve into a line that forms a giant cold pool of air. That's a giant downdraft that travels along with that line and just behind it. And it acts as a wedge and forces the warm, humid air ahead of it up and over the top of it. And that helps to form this very, very distinct cloud feature that you see in the video here called the shelf cloud. That is the leading edge of the cold pool of air. The process of downdraft and outflow is what dominates in these storms, when these lines of storms. Whenever you see a shelf cloud with a line of storms, first get your app out, look at it and say, yeah, okay, it's a line of storms. And then you'll see in the reflectivity signature, this so happens to be a bow echo, where the strongest winds are going to be near the apex of that bow. But you're also going to see a shelf cloud approaching. So when you see a shelf cloud, think downdraft, outflow, damaging winds. I've got to be the sort of the thought process with lines of storms, and when you see that shelf cloud as well. The shelf cloud acts like it's sort of a wedge. Again, it's sort of the leading edge of the cold pool of air down near the surface, and that wedge of cold air actually forces the warmer, humid air out ahead of the line, up and over, and forms new updrafts on the leading edge here on the east side of the line. And that's how these things live and how they move and how they regenerate as they move along, is new storms form along the leading edge of the line as that colder pool of air and the strong winds undercut it underneath, and the movement of the storms kind of attains sort of a steady state or a balance. Um, and they can last for quite a while and produce damaging winds along a very, very wide swath sometimes with these squall lines. Oftentimes in Kansas, the majority of damage every year is due to damaging straight line winds that may be associated with lines of storms, not necessarily tornadoes. Shelf clouds also, again, here's an example of a shelf cloud higher base. This is out in western Kansas, I think. And what we're seeing here with the higher bases is underneath it, what do you notice? There's a lot of blowing dust. And this is pretty common with the leading edge of the cold pool of air, the downdrafts and along lines of storms. You may see the shelf cloud, and then along the leading edge of the shelf cloud or just behind it, you'll see a lot of blowing dust that's blowing out away in the direction of the storm's movement. And sometimes that can fake people out because some of these can turn into little eddies that spin, called gustnadoes, and they can look like tornadoes. I'll show you an example of one that somebody thought was a tornado here a little bit. But sometimes you can see scary looking clouds, some tornado lookalikes with shelf clouds that aren't. Here's a movie of a shelf cloud. The rain is behind it, the cold pool of air, and you actually notice a lot of low-hanging clouds here just behind the shelf itself. These are scud clouds, stratocumulus under deck, the acronym, and they look kind of scary, but oftentimes they're just associated with rain-cooled air that's being pulled up or maybe pushed back down by the downdraft and updraft. They are not associated, in this case, with any sort of persistent organized rotation, but they're oftentimes found with shelf clouds as well. So gust fronts and lines of storms, the shelf clouds. Remember, it's the leading edge of a downdraft and cold pool. That shelf cloud's a very, very large, narrow cloud. It's produced by that cold pool of air, the gust front, and they're very common with lines of storms as well. And this is what they look like. You've seen them before if you lived in Kansas or anywhere in the Midwest. These are very, very common. We do get questions. Can you see gust fronts on radar? And the answer is sometimes yes, you can. This is called radar reflectivity, and it's basically showing us where there's some rain or maybe the intensity of the rain from the yellows and the reds. But it also shows us here in this case that this is an area of storms that looks to be dissipating and is actually collapsing, and actually it's actually produced a gust front, a very, very an area here where you have winds that are accelerating outward away from the collapsing storms. And you can see that on radar sometimes. If it's close to the radar, you can see the outflow boundary. Now, why is this important to know? Well, if I've got some sort of a concert going on and I've got a stage set up and I can see something like this coming, that's important information for people to know, because this may be the leading edge of 50 to 55, 60 mile an hour winds. And I want to watch this and not necessarily this red stuff to keep people safe and get them away from the stage. And so, yeah, sometimes you can see these outflow boundaries and these gust fronts on radar. Just in certain situations, you're able to do that as well. All right, so let's talk about supercells. And we've got another poll. We're going to try another poll here. Go ahead and launch the next one, Adam. What percentage of supercell thunderstorms produce tornadoes? What do you think? All right, looks like we've got the responses here. And we got a pretty good group here tonight. Must be people from Kansas or around the area. Most of you said 25%, and that is correct. One of the things about supercells is that the majority of them do not produce tornadoes. It takes the right environmental conditions, and specifically it's the low levels, very low levels in the lowest few thousand feet, where we need just the right amount of spin in the atmosphere. And that comes from, that can come from warm fronts. That can come from the changing of wind speeds and direction in the lowest few thousand feet, and the right buoyancy as well. The thing about these supercells is they are prolific hail producers. Just like last Wednesday night, if you were here in this area of the state, not only were those supercells producing tornadoes, But what was much more common was they were producing very, very large hail all over the place. In fact, most of these supercells, or all of them, produce some sort of big hail, either the size of golf balls, ping pong balls, or larger. We had some baseballs and softballs as well. But the supercells, they can also produce the strong and violent tornadoes in the right environmental conditions. These are characterized by their rotating updrafts called mesocyclones. They rotate because of wind shear, and I'll talk about that here in a little bit. So the next slide here, and I'll let that get over here. When I say wind shear, what do I mean? I mean that the winds at 15 to 20,000 feet might be 100 miles an hour. The winds at the surface may be 30 miles an hour. And so there's a change in wind speed with height. That causes the storm, to believe it or not, to tilt over. And because it tilts, the rain and the hail actually falls a little bit downwind of the updraft itself. The updraft and downdraft remain separate, and it allows that storm to live a lot longer than other kinds of storms. And then the other one is the change of wind direction with height, especially in the low levels of the atmosphere. That can really enhance your wind, your spin in the lower part of the atmosphere. That creates these little tubes of spin that get tilted into the vertical. And the more spin you have, especially in the lowest few thousand feet, like along warm fronts, like we had last Wednesday, the quicker these supercells can actually ingest that spin and get tornadoes to form, if you have the right mix of buoyancy in the low levels and moisture as well. And that's what we had last week. We had the directional shear in the vicinity of that warm front, and we had the wind shear. We had supercells that not only were producing big hail, but also tornadoes. Here's a backyard experiment of a lack of wind shear. In other words, the updraft goes up and goes straight back down and collapses back down on itself. If we're viewing this from the east looking to the west, look at this. Now the winds aloft are stronger. And so here's our updraft, and all the rain and hail gets dumped downwind. That's what it looks like in a backyard. This is what it looks like in nature. This is the rotating updraft of a supercell thunderstorm. We are looking west. Our perspective is very important around these storms to understand what it is that we're looking at. This is that big spaceship saucer looking rotating updraft called the mesocyclone. The air is going up. Because of wind shear, the air is going down over here off to the right where the rain and hail is falling. And so that is the benefit of wind shear for these supercell thunderstorms as well. Here's another example in the field. This is a classic example, maybe a wet classic supercell thunderstorm. We see this very, very distinct rotating updraft right here, and then the rain and the hail off to the right, right there, and then the updraft itself, kind of smooth looking. It just looks weird. When you see things like this, it's going to jump out at you, and you're going to say, yeah, that's probably one of these mesocyclones, rotating updrafts. The updraft base is right here as we look to the west-southwest. The lowering, called the wall cloud, is right in here. Now, what discriminates or separates that 25% of storms that do produce tornadoes from the 75% that don't? It's that low-level rotation. In other words, the low-level rotation you see is sort of the visual evidence of some of that very, very strong low-level spin being ingested into the low levels of the thunderstorm itself. And so that's sort of a red flag. If you see low-level rotation in the vicinity of the updraft and the lowering, that is a red flag that we've got one of these storms that may be in the right environment to produce tornadoes. Now, a lot of people say, wait a minute, I'm confused. I see a lot of rain back here. You said that's the updraft, and you're saying that, but I see a lot of this big rain shadow, dark area back here. There's a lot of rain. Yeah, you and I are right here. We're sort of in the O of the of, and we're looking to the west-southwest. Here's a radar reflectivity signature of a supercell thunderstorm, and it has that characterized or characteristic hook shape to it. That represents the process of rotation. And this red stuff and yellow stuff, that represents rain or maybe the presence of hail. This is what you see. This is the radar indicated hook echo. Some of this rain and hail over here to the right is being wrapped counterclockwise behind the updraft and then downward into the backside of the base of the updraft. That is the radar indicated hook. This is the rain that you see associated with that. And near the tip of the hook with classic supercells, you'll see a lowering, and that's where you may get a tornado. The separation of these storms is unique in the sense that it allows supercells to live a long time. Here's an example from Mississippi, Alabama. It's nothing, it's really pretty typical to see supercells in Kansas develop along the dry line, say, I don't know, around Hutchinson, maybe Russell, Great Bend. And then those supercells will move east northeast and track across northeast Kansas over the next 6 to 8 hours. That's pretty typical. They last a long time. And one of the reasons they last a long time is that they are separate. The updraft and downdraft are separate. It allows them to live a lot longer than other types of thunderstorms as well. I mentioned that thunderstorms breathe, supercells breathe a lot. This is a really dramatic example of a high precipitation supercell. I mentioned dew points. Dew points in the 50s, mid 50s is what we had in March. Once we get into May and June, we'll have dew points in the 60s, maybe the 70s. And when that happens, we get what we call high precipitation supercells. These are nasty. They're nasty because the contrast that allows you to see the important features like lowerings and wall clouds and tornadoes, it all becomes more difficult because there's so much rain wrapping around the thunderstorm, and the cloud bases tend to be very, very low. These are dangerous. If it is producing a tornado, oftentimes it's going to be wrapped in rain, and you won't be able to see it anyway. But the inflow tail cloud that you see right there, that is the storm taking a deep breath of very, very warm, humid air, and that goes into the updraft, and you can see the updraft rotating here very dramatically. Good luck in trying to spot this. You'd have to go probably up to the top of the hill there and look back to the west-southwest in the direct path of the high precipitation supercell. That's a dangerous proposition. Don't do it. HP supercells look different on radar as well. The radar image, instead of a classic hook, has more of a kidney bean shape sometimes to it, or it just has a notch on the front side. And it is that notch area where the updraft is strongest. And sometimes you can get the tornado located in that area of the thunderstorm with these HPs as well. They're just nasty. They're nasty because they're difficult to spot. Here is an example from May of 2019, where this is Highway 59 looking north to Lawrence. And this is what looks to be just a giant rain shaft, right? Well, certainly you're looking at the radar reflectivity. It looks like a blob. It doesn't look scary like a classic hook echo. But in fact, right in here, there's a large tornado on the ground. It is a strong, borderline violent tornado moving across the southeast part of Lawrence right now. You can't see it with the naked eye because it's wrapped in rain, and that's what these HP supercells do sometimes, is they mask the tornado from you so you can't see it. Sort of a review, we'll take a step back here and review some of the terminology with supercells. What you're looking at right here is sort of a schematic of a radar reflectivity image, what you might see with a radar reflectivity image of a classic supercell. The colors indicate the intensity of the rain, light rain, maybe the heavier rains, the presence of hail in that area. The shapes indicate the presence of the process of rotation counterclockwise. It may take on a hook shape right here. The rotating updraft cloud called the mesocyclone, it's this white area right here. It's out in front of the reflectivity signature that you see on radar. So in other words, that crazy flying saucer shaped cloud that is rotating is out here in front of the radar reflectivity signature that you see on radar. You may see a lowering in that area. The wall cloud may be in that area. You and I want to be, if we can, 2 to 3 miles or so east-southeast of this area and the inflow region of the thunderstorm, because it offers the best vantage point and the safest area to see the important low-level features within that area. That's where you're going to see the possible tornado in that action area of the thunderstorm. That you may see a lowering in there. Where both of these cases, we're looking to the west or maybe the west-southwest. In both of these cases, there's the base of the updraft, and there's a lowering underneath the base where you have the strongest portion of the updraft. That's a lowering. That's a wall cloud. These are very, very common. They're not. I would tend to. They're not all that special, really. A non-rotating wall cloud really is pretty common. It's the rotating wall clouds that should really raise the red flag that you're dealing with something that's a lot more potentially dangerous to produce a tornado. Obviously, looking for that, use it as a landmark. If you see a lowering underneath the base of the updraft, and watch it. Watch for signs of rotation developing and organizing, rotation or rising motion into that cloud. that persists at least 10 to 15 minutes. And then as a spotter, if you're out there, you start to feel an increasing wind at your back that's pointing towards that area of the storm. That's sort of another thing that you can remember and to think about, that storm is taking a deep breath of air, and the inflow and the updraft is probably strengthening. And so that's another characteristic of these storms that can give you an idea of what may be going on and what might happen in the near term or in the next 15 to 20 minutes of the storm. Here's a picture. We're looking west here. Here is the rain-free base of the updraft. Here's a lowering, sort of a schematic for the lowering here. And what happens is some of the rain cool air gets pulled up and into the updraft, and it forms this cloud lower down. Sometimes it slopes down towards the rain area as well, and sort of develops a tail off towards the rain area. Again, we're looking to the west, and so our perspective is really important when it comes to understanding what it is that we're looking at. This is sort of a very obvious example of a lowering here, high base, very high base. The rain and hail is off to the right. The updraft base is right here, and our lowering is right there. It's sort of a very obvious case. This is probably another more common case we would see in Northeast Kansas. We're looking to the northwest. We see what we call the updraft base right here, and then we see the lowering underneath the sort of cumuliform looking updraft base above it, where you see what almost looks like more cumuliform or cauliflower-like appearance to the cloud features above. And so watch that area, use it as a landmark, look for signs of organized persistent rotation about a vertical axis. Funnel clouds, these are going to be obvious, smooth. Sometimes they're smooth and laminar. They're going to be rotating. The circulation comes into contact with the ground. It becomes a tornado. Sometimes the funnel is not in contact with the ground, but you look below and you see some dust whirls or debris underneath that circulation or underneath that funnel, and that can be indeed a tornado that's on the ground. Sometimes you don't need that classic condensation funnel that extends all the way to the ground to get a tornado. Now, sometimes you got to be careful. I mentioned before there are tornado lookalikes out there. One of those is scud clouds. What the heck is scud? Scud are scary looking clouds or SLCs that hang down, and they can be associated with the updraft area. They can be in the downdraft area. These are not rotating. They just look scary. And if you see them. Watch for signs of organized persistent rotation about a vertical axis. Here is a video example of, we're looking to the west. And if I saw this, I would say, well, that looks curious. It looks like a weird cloud. I'd pull out my radar app and I'd say, what kind of storm am I dealing with here? And it looks like we might have a shelf starting to develop, maybe a bit of a weak shelf cloud here with some rain behind it. So maybe there's a cold pool developing, and some of the rain cooled air is getting tugged up into that updraft area. I would just watch it for 5 minutes. Watch it for a few minutes. Look for signs of organized persistent rotation. Oftentimes within a few minutes, you'll realize, no, this is not rotating. It's not important, at least when it comes to whether a tornado is going to develop or not. There's a lot of this stuff out there. You'd be surprised. And there's our guy that you'll see again here in a little bit. Scud clouds, there's oftentimes little or no actual rotation with these, but there's more turbulent motion up and down. Sometimes they can form into a wall cloud underneath the updraft. Like I said before, they can be in any part of the thunderstorm. They can be associated with the downdraft area, the shelf cloud, and they can be found in between the updraft and downdraft. Just watch the clouds and use them sort of again as sort of a tag for the motion and the processes that are going on in the thunderstorm as well. Augustnado. People think that I made this up. It's not a made up word. It's real. These are little eddies or little vortices that form along the leading edge of the cold pool of air that can look and really freak people out because they're spinning and they can form on the leading edge of the cold pool with a shelf cloud. But they're not tornadoes. They're not actually attached to the base of the cloud. Watch these for as long as you can to get a good sense of the motion. You'll see the feature moving along or ahead of the gust front away from the storm, the precip area. And I'm going to show you one right here. This is courtesy of Drone Lawrence, Topeka, or dronelawrence.com. Go check them out. They do some fantastic work. They've allowed us to look at this. This is a storm that moved across Topeka into Lawrence on July 14th last year. And as the drone is panning, we're looking to the south right now. Now we're panning to the southwest. And the cloud feature that jumps out at you should be this elongated, narrow cloud. It's sort of a shelfy appearance to it. Um, Wait a second. What the heck's going on over here? We're going to keep playing it, though. We're going to pan to the west and now the northwest. And again, the cloud feature that jumps out to me right away is the shelf cloud, which again suggests the process of downdraft, outflow, cold pool of air has helped to form this. And so there's likely a cold pool of air and some damaging straight line winds coming towards us as well. But let's take a closer look at this thing. This is there's our guy again. This was reported as a funnel cloud. It was reported as a tornado. It was neither. This is some blowing dust. This is pretty typical of what you see on the leading edge of these cold pools with shelf clouds. And sometimes this blowing dust gets pulled upwards towards the leading edge of the updraft. And believe it or not, sometimes it'll start to spin like a little eddy in a stream. And when that happens, people really get sort of worked up and think that we've got a tornado, maybe it's a squall line tornado, things like that. It's not. It's, again, not attached to the base of the cloud, but these things can spin, they can look weird. Again, watch the motion of it. It's blowing away from the storm along the motion with that shelf cloud, the cold pool of air. But these are pretty common, especially out in areas where we're getting dry now again. And so if we were to see a shelf cloud move through some gusty straight line winds, we'd probably have a lot of blowing dust out there. Gustnadoes are out there. I don't know, dust devils, but scud clouds, scary looking clouds that are hanging down. You can see those associated with shelf clouds. Sometimes rain shafts can look weird. Smoke plumes as well this time of year can get drawn up into thunderstorms. It sounds strange, but it's true. That can happen. The key point is if you're unsure of what it is you're looking at, just take the extra few minutes to watch for signs of organized persistent rotation. Ask yourself, looking at your radar app, is this the kind of thunderstorm? Is the updraft area correct part of the thunderstorm that I'm seeing, or do I just see cold air rising with scud? And then again, the gustnadoes will move with the outflow and the gust front away from the thunderstorm. Real fast, I want to talk about the basics of radar, how it works. Radar will send out a beam of energy beginning at about a half degree above the horizon. Excuse me. I got a frog in my throat there. So radar basically will do a 360 at a half degree above the horizon and go up and do it again and do it again and do it again. We have the ability to force it to go back down to a half degree when we're in the severe weather mode, so we can see the important low-level features that may be associated with tornado formation. But based on whatever's out there, the radar will send us or the energy from hail, rain, maybe it's debris, will scatter back to the radar, and that radar will paint a picture of colors and shapes for us. This is reflectivity. This is what you're most used to seeing on television, on the web, on your radar application. This is the amount of energy that's getting scattered back to the radar, and it indicates, in this case, maybe the presence of hail or rain, the intensity of rain, and then these brighter colors, the pinks, maybe the presence of hail as well. And the shapes, I mentioned before the hook shape. In this case, there's a little bit of a hook right here. This suggests the process of counterclockwise rotation. Does the hook echo mean that there is a tornado? No, it doesn't. It doesn't guarantee that there's a tornado on the ground. It only means that we have counterclockwise rotation in this part of the thunderstorm, and there may be what we call a rear flank downdraft that's cutting into the backside of that updraft in the vicinity of that part of the thunderstorm. And so it's certainly a red flag that you got to watch for other things like velocity data, which we have with our Doppler radar, and we can tell the direction that the rain is moving, the wind is moving within the thunderstorm. It's like an MRI for a thunderstorm. We're able to tell the velocity of the data, or the velocity of the rain and hail, the winds within that thunderstorm. And based on the colors, the warmer colors are winds away from the radar. The cooler colors are winds towards the radar. So in this case, we have away towards the radar is down here. And so we have counterclockwise rotation right here, hot off the press. This is a animated loop. Hopefully you're able to watch it. It's radar reflectivity and velocity data from last Wednesday. This is this circle near Alma. This is Alma, Kansas, not too far west of Topeka, Kansas. This is Wabunsee County, and this is the supercell thunderstorm, the reflectivity on the left, and the velocity imagery on the right of the thunderstorm that produced what was the strong tornado just to the south of Alta Vista, Volland, and thankfully dissipated just to the south and west of Alma before it got there. This is the way it looks with the velocity and the reflectivity together. We're able to tell, yeah, indeed, there's certainly a hook echo, and it wraps around itself a couple of times. So that tornado was wrapped in rain, likely, at least for a time. And then the velocity data here, it's hard to keep up with it, but the cooler colors are winds towards the radar. The warmer colors are away. We have a tornado circulation with that storm there. It's an example of what we see on radar. Sometimes people can't see the tornado. Sometimes it's wrapped in rain with these HP, these high precipitation supercells. And sometimes the radar can confirm for us there is a tornado inside that rain shaft and it's doing damage. On the left, we see the radar reflectivity. In the center image, we see the velocity. The cooler colors are towards the radar. The warmer colors are away. We have counterclockwise rotation in this part of the thunderstorm. And then in this radar data right here called the CC, the correlation coefficient. Don't worry about the technical term. Basically, the takeaway is that the radar is looking at the scatters out there, and it's saying, well, that's rain. Those are raindrops. Those are hailstones. I don't know what in the world this stuff is because none of it is the same shape or size. It's all sorts of different shapes and sizes. It assigns a value near 0, which shows up as a blue little area in what is a sea of maroon. When we put those three signatures together, either a hook and then the velocity imagery along with this, that's a tornado debris signature. That's a signature. Radar is telling us there's a tornado on the ground. It's lofting debris maybe 10 to 20,000 feet into the atmosphere. Why do I mention it? I mention it because it's something that can give people extra information, and we'll put it in our warnings as well. And not only that, but the media partners are talking about it as well. They were talking about it in May of 2019. This guy's name is James Spann. He's down in Alabama, but everybody's talking about it. When one shows up, you will hear your media partners talking about these tornado debris signatures. And the reason they're talking about it is to confirm for you, yeah, this is on the ground. It may not be seen by a human being, but the radar sees it. It's happening to help people facilitate the sheltering process and get them into shelter a little bit faster than otherwise. So warning decision-making, how does this work? It's 3 legs of the stool. It's knowledge of the near storm environment, things like low-level wind shear, buoyancy, radar signatures, and input from spotters, chasers, human beings around the thunderstorm. It can be reports, it can be streaming video. And based on all of that, we will make a decision about whether we warn or not. All of this information tells us what's happening around the thunderstorm. And on Wednesday, based on the near storm environment and the radar signatures, we knew these thunderstorms were going from moving more north to more northeast. And that's when the tornado risk was starting to increase quickly. And in fact, in the streaming video that we saw, that was confirmed for us, and we were able to issue those warnings before the tornadoes form. That's sort of an example of how this kind of comes together. And it's the ground truth. It's what gets everybody's attention. When human beings see something and report it, and it gets out to the media, it helps that facilitating that sheltering action faster than might otherwise be the case if it just said radar indicated. Where should we be viewing these supercell thunderstorms from? The inflow area, the inflow region of the thunderstorm, which is to the southeast, east-southeast by a few miles of the thunderstorm. It gives you the best vantage point for the important features, least chance of encountering very bad things like large hail, the tornado itself. And generally speaking, the tornado is going to stay the same distance away from you. It won't get too much closer to you. And in fact, it may move a little bit further away from you. This is an example of that. The tornado may be near the tip of the hook with these classic supercells. We're viewing the tornado from the southeast, looking northwest, and here it is. Good contrast here. We're able to see things. It's clear. We're in a relatively safe spot here. No danger from the tornado hitting us because it's moving parallel to our position, or maybe even a little bit further north and west away from us as well. Now, as that tornado really wraps up, we may be in a different position here. Now we're actually just to the southwest of the tornado, and we're in what we call the rear flank downdraft area. And you can get buffeted by very strong damaging winds in this area. And the other thing that happens in this area is the rain and hail that make up the hook on reflectivity may start to wrap around between you and the tornado itself, such that you lose sight of the tornado. And that can happen in what we call the RFD area of the thunderstorm, of the supercell. And so that's something that you want to keep in mind as well. As it's starting to move away from you, you may lose sight of it. The most dangerous spot to be in, the bear's cage, the vault area. This is not a good place to be, not a smart place to be. You have chances to encounter large hail, damaging your car. And oftentimes, if a tornado is on the ground, these tornadoes can take sharp left turns, north turns, and often do. And that puts you in the direct path of that tornado. And so these are dangerous places to be. You do not want to be in that area of the supercell thunderstorm. If I have a choice, I want to be one of these three people here in the inflow region of the thunderstorm. Again, it gives you the best vantage point, the safest spot, offers you a good escape route to the south or east to get away from the storm. This is an example of a lowering called the wall cloud that you may see from the inflow region of the thunderstorm looking to the northwest. What to report? Obviously, tornado, funnel clouds, rotating wall clouds. We'll take hail of any size. It doesn't have to be necessarily greater than 3/4 of an inch. We'll take any hail you got because it helps us calibrate what the storm is doing now or was doing when it was over you, and what it may be doing now. Any sort of wind damage, wind gust estimates, flash flooding. When I talk about all the different thunderstorm-related hazards tonight, it is flash flooding that kills more people every year in Kansas than any other hazard, at least in the 10 years. The last 10 years, we've lost, I think, 7 from flash flooding. It's usually vehicle-related, driving into flooded roads. When it comes to wind, estimating a 60-mile-an-hour wind, people ask, how in the world do I do that? A tree branch about the size of your wrist can be an approximation for a 60-mile-an-hour wind. Otherwise, looking for damage, tree limbs, so on and so forth, is another way to do it. And reporting damage into the National Weather Service can be very helpful for us to know and confirm for us what we're seeing on radar and anticipating that the storm is doing based on the environment as well. Guess the wind speed. I've got a couple of videos for you. This is not a poll. Let's just go ahead and watch the video and give me your best guess of what you think that wind speed is. What do you think? It looked all right. I don't know. When I estimate wind speeds, I like to do it in 10-mile-an-hour increments. And so this is a little hard here, just having one value to maybe approaching 60. I mean, that's probably pushing it because I didn't see much in the way of tree limb or any sort of damage here. It looked like a healthy storm. I would probably report 50 to 60-mile-an-hour winds with this, but not higher than that. I wouldn't go higher. Maybe up to 60. How about this one? Adam Huffman, you are correct. It is at least 80 miles an hour. I don't know. It could be 90. It could be 100. I don't know. I haven't experienced winds that frequently, that high to really have a good feel, but it's bad. Obviously, if I was making a report, I'd say at least 80, probably higher than that. That's pretty bad. These are derechos. These are very, very long-lived, very damaging wind, straight line windstorms. They can really mess up a huge swath of territory with 100-mile-an-hour winds. That was an example from, I believe it was, well, no, it was somewhere in Iowa in the last several years. When it comes to hail, report hail size and things that we're familiar with. Obviously, this is sort of the measurement and then the equivalent thing that we're familiar with. Worked in an office in the past where the guy wouldn't report golf balls. He would report Oreo cookie sized hail. I guess that's the size of a golf ball. You can do that if you want. I don't know. It's up to you. But we ask, and we'll take any size hail. I said that before. The severe thunderstorm threshold is 1 inch quarters. We'll take any size hail you got because it helps us calibrate what the storm was doing in the past and what it may do in the future. The supercells we had last week were producing baseballs and softballs that were pretty common. And that's nasty. That's what these supercells do. They are prolific hail producers. Flooding, obviously, water over roadways, closed roads, things like that. This is information that we can get into the Weather Service, then turn that around and get to the media partners and push out so that they can close the roads, or obviously that the inter county communications, they can get out and close those roads so people don't drive into them and get themselves into a world of hurt. What to report, what, when, and where? What is the hazard? Where and when did it happen? Important information. Seems kind of silly to highlight this, but it is important information. How can you submit reports to the National Weather Service Topeka specifically? X, formerly known as Twitter, is a very useful platform during severe weather. Why? Because you can tag us. When I say tag us, you can just do an @NWS Topeka and then enter your report. Or you can use the Kansas weather hashtag. When I say hashtag, it's this little number sign, KS weather. We're monitoring both of those. And so in real time, we would see the report and be able to get that in and pushed back out. And those are other information or other ways, Facebook, email as well. So real fast, severe weather safety, I would be remiss without saying this. Tornado safety, get as low as you can, put as many walls between you and the outside as possible. If you have a basement, obviously that's the best. Get underneath something sturdy, cover up with something heavy. We talked about worst case scenarios, helmets, protect yourself from blowing and falling debris. If you don't have a basement, interior room on the lowest floor, oftentimes even in strong and sometimes violent tornadoes, there is a room on the lowest floor that's standing when the rest of the walls have been taken away. And it sometimes is an interior bathroom on the lowest floor that's anchored by the copper plumbing in the walls. It's still there where the rest of the home is gone. And plan ahead. For those of you that live in mobile homes, vulnerable population, know where you're going to go and how long it takes to get to your shelter. Here's another way to look at what I just said. Obviously, bring a phone, put shoes on, head protection. Think about your kit. Have a kit already put together in your shelter location so you don't have to think about grabbing everything and going. Have it all ready to go. And so, again, I think if you're from this part of the country, you've heard this before many times, but it works. People survive violent tornadoes. I saw in 2016, incredible case just southwest of Chapman of a strong EF4 tornado. It was getting close to 5 based on some of the damage it was doing. Wiped a poured concrete foundation completely clean with some of the debris still standing or just tossed adjacent to the home. A woman was home in this structure and she walked away. She was in the basement. It's pretty amazing to see. So this stuff works. It does. It's our best bet to protect yourself in tornado situations. You know, tornadoes and cars, it's always a difficult answer when people ask the question, because the answer is it depends on your situation. What you should do is depends on what sort of a situation you're in. In May of 2016, people that were in the path of that big tornado in Dickinson County actually got in their car and left because they could see the tornado coming and they didn't want to stay. And people do that in rural areas. It works. And other times in populated areas in Oklahoma City 10 years ago, it was a disaster. If you can't see the tornado, you don't know where it's at, get to a sturdy shelter as fast as you can. And these absolute last resort scenarios are absolute last resort scenarios. They're sort of like you're in the ocean and there's a shark. What would I do? You can punch it in the nose. Well, I don't want to be in that situation. I want to do everything I can to avoid that situation, and maybe not be in that type of a situation. And we talk about the importance of that with the additional information that's available nowadays in the form of radar and watch information. All this information is available to us in our hand on our phone so that we don't get in a car into a situation like this. And when a tornado is nearby and you have to make a crazy decision about jumping out of your car at the last moment. Tornadoes in mobile homes, this one's pretty clear. They only make up about 5% of the housing stock in the United States, but the majority of tornado fatalities still occur in mobile homes. You got to leave. You cannot survive a strong, obviously, or a violent tornado in a mobile home. You got to go somewhere else. Community shelter, ideally. And if you don't have one, a friend or a neighbor that has maybe a wood frame home or a basement that you can go to. Have a plan in advance that looks at where you're going to go, what you're going to do. This was only an EF0 tornado that did this damage. And you see this a lot. The anchoring, mobile homes fail from the bottom up. And when I say that, I mean it's the anchoring or the lack of anchoring that occurs with these structures. And it only takes maybe an 80-mile-an-hour wind to roll them. When it comes to tornadoes, they are damage indicators. Mobile homes are, but the degree of damage does not extend beyond an EF2. In other words, once you get to 115 to 120 mile-an-hour winds, mobile homes are destroyed. They're gone. There is no EF3 damage to a mobile home. It does not exist. And so that's the important point. These are vulnerable populations, and probably the scenario we worry most about here in Kansas with the mobile home communities is making sure that they get to their shelter if they have one, and they can get to one if they don't. We worry a lot about this because they are very vulnerable to strong and violent tornado if they're in the path of those. And so this was what I mentioned before. They make up the majority of fatalities across the country. Now, the EF scale real fast. What is this? This is the damage intensity scale. In other words, after a tornado happens, we will go out, we will look at the degree of damage done to what we call damage indicators, stuff that's in the path of a tornado. It can be trees, it can be homes, it can be power line or power poles, anything that humans might build that are in the path of the tornado. And then based on the degree of damage to that structure or that damage indicator, we will it will provide a wind estimate for us. And then based off the construction quality of that home or that structure, we'll maybe go on the high side of that range or the low side of that range. And so a lot of people sometimes they'll say, they'll see a wedge tornado and they'll say, well, that looks like a violent tornado, but it was out in the middle of nowhere and it might have only chewed up some trees. And we go out and we do an assessment on that, and it is rated an EF2. And people will say, how in the world can you do that? Well, it's the methodology. It's a damage intensity scale, and it depends on indicators or stuff being in the path of that tornado. And so that's how it works. The majority of tornadoes are EF0s and EF1s. The killer tornadoes, 98% of the fatalities are EF2s and greater. And so that's how that works. That EF scale is a damage intensity scale. Flash flooding, don't drive through water. It only takes a couple of feet of water to make a car buoyant. And if that water is flowing and has a current, you're going to go with it. And that's how the fatalities happen. Most of the flood deaths are occurring at night when people drive into flooded roads. They don't realize how deep it is, or they see somebody else that tries to go through it and they do the same thing. I mentioned this before, and it's pretty clear. Flooding across the country takes far more people than tornadoes do every year, almost twice as many. And most of these are people driving into flooded roads, vehicles at night. The good news is most people, the data that we see, the lightning fatalities and injuries are both going down quite a bit over the last 20 years. And that's because to keep yourself safe from lightning is easy. Just get in your car, roll up the windows and keep your hands inside. The body of the car acts as what we call a Faraday cage, protects you from the energy of the lightning. So even if it strikes your car, that energy goes through the body of the vehicle and not through your body. And so just get into a car, roll up the windows, keep your hands inside if you can't get into a house or an enclosed shelter. And if you hear thunder, it's time to suspend play and take shelter. That has no doubt saved lives over the years. Most people that get struck, though, they do live. But you don't want to risk it. Certainly, when you hear thunder, get indoors and wait until the storm has passed as well. All right, we're pretty much at the end here. It's gone about hour and 15. Real fast. Fact or myth? It's not a poll. You can just answer it in your own head or in your house. Just shout the answer if you like. That is a fact. May and June usually is our peak 2 months for tornadoes here in Kansas. Council Grove, you don't get tornadoes because you were protected by a valley. You're in a valley. Is that true or false? No, of course not. That's not true. Nobody is protected by a river, hill, valley, stuff like that. That's all myths. It's just that you haven't been hit by a tornado yet, and someday you will be. If I see a tornado when I'm in my car, I should get underneath an overpass. I think we've beat this one pretty good over the last 20 years. Obviously, the answer is no. You don't want to do that because it acts like a wind tunnel, and actually creates a more dangerous situation when you do that for getting hit by debris and getting taken away by the winds. You don't want to do that. Best place to go in a basement, it's the southwest corner. No, that is not true. It was that was the message when I was growing up. It was to open up your windows and then get in the southwest corner of the basement. And both of those are not true. Getting in the basement is a good thing to do, but just get into whatever part of the basement you can, get underneath something sturdy, cover up with something heavy. Ironically, it was the 1966 Topeka tornado that provided some evidence to suggest that you do not necessarily want to go to the southwest corner. There was no rhyme or reason with some of the homes that were destroyed around Washburn University in Topeka. When looking at the debris pattern in the basement, you just want to get as low as you can and get underneath something sturdy, cover up with something heavy. And yeah, don't bother to open your windows. That only allows the wind to get into your structure. And when the wind gets in, it's going to try to find a way out. And that usually means it's going to punch its way out through an opposing wall or lift up the roof. And that's a bad thing. Real fast, tornado lookalikes. None of these are tornadoes, but they sure look like it in the stills. I don't have video of it, but these are scud clouds here. Look like funnels based on the lighting. More scud. That's not a wedge tornado. Looks like a sort of a scud, or maybe even a little bit of a shelf that might be moving over the top of us. Those are rain shafts in the bottom left. And that's some smoke from a fire or maybe a refinery. Looks like that's getting drawn up into the updraft region of a legit thunderstorm. That is an updraft. And there's legit scud hanging off of that. So we've got, you can actually use that as a markers or tracers for the winds that are going up and into that thunderstorm there. But that's not a funnel or anything like that. What's the best storm spotting location? It's C. If I have a choice, I want to be in that area because it offers the best vantage point for the important features. And if I have to get away to the south and east, I can do it. The most dangerous, obviously, you don't want to be in the vault area, the bear's cage, they call it. You don't want to be too close to that, especially in the path of the tornado. An extremely dangerous place to be. True or false? A watch is issued means that you should go to the basement and take immediate action to seek shelter. No, that's, hey, heads up. Storms may develop over the next few hours. So if you had a plan to drive from Topeka to Salina, you either want to watch your radar app or maybe delay those plans because supercells might develop from Concordia down to Dodge City and then move northeast and produce baseball-sized hail. You don't want to be on the interstate when there's baseball-sized hail. That's what a watch is. What kind of cloud feature would you see if you're located at X, the giant yellow X? There it is, the shelf cloud. It's the leading edge of the cold pool of air, the gust front, with that line of thunderstorms that is driven by that giant cold pool of air, process of downdraft and outflow. Is this a good report? Relatively speaking, I appreciate that they sent the image in, but I have questions. And some of those questions are, where are you? When was it taken? Or when was it taken? And who are you? Where are you at? So it's not a great report. I appreciate them doing it. But again, the what, where, and when can be added to that report as well. Okay. I think we've reached the end here. If you're interested in becoming a volunteer observer, spotter, you would be put into our database. And then if we see bad things, you could call us, or we could call you and ask you maybe how bad the hail was, how big it was, so on and so forth. You can go to our website, and on our spotter show schedule link, there is a web page And on that webpage, there's additional spotter information that'll take you to where you can go and take additional training. And once you do that, your information then gets forwarded on to us, and then we'll get in touch with you as well that way. Holy cow, that was a lot. About an hour and 20. We had some technical glitches. We figured those out, it seems. I appreciate everybody hanging with us. Most people did, and I appreciate that. And so with that, we'll end. If you have any questions, we'll do our best to answer those here. Adam and I will answer the questions when we can. Otherwise, thanks for coming. I appreciate it.